All right, kiddos, let's talk a little bit about how we would name aromatic compounds tonight. This will sort of be one of our last sections of just pure nomenclature. We're going to go back and do some reactions, and then we'll sort of come back and do nomenclature for the other functional groups once we've got a few reactions under our belt as well. I didn't want to overwhelm you with one or the other at the same time. So aromatic compounds, remember, are those that contain a benzene ring. Benzene is a pretty interesting compound. Actually, the development of what does the structure of benzene look like was kind of a big deal back in the 19th century. It was proposed by a guy named August Kekule, and he's a really big deal. He had 3 students that went on to win like 3 of the first 5 Nobel Prizes. So kind of a big deal in chemistry circles. He's also the same guy that came up with the idea that carbon was what he called tetravalent, meaning that it could essentially have 4 bonds, which of course we know is sort of the centerpiece for us in organic chemistry, is that tetravalent structure that allows those 4 bonds is what allows us to form these really long chains. And so Kekule is the guy that says, hey, he's got this weird molecule of benzene, and they're trying to figure out what the structure is, and really structural chemistry sort of comes about partially because of what this guy does. And essentially his idea is that, hey, I think that maybe benzene is in this ring, this sort of hexagonal ring of 6 carbons, and then that there are alternating double bonds within that ring that explain the structure that he saw. And remember, he's not actually seeing any structures. Like when we get into the 20th century, we've got some techniques like X-ray crystallography, and then some of the stuff that we'll talk about later in the year, like our IR spectroscopy and those kinds of things, that we can actually figure out a little bit about the structure. Back then, they're pretty much just doing wet chemistry. They're just doing reactions to figure out what the structures of these things look like. And so it's kind of a big deal back in the day. What Kekule also proposes is that it's not just that you have one structure with a double bond, that what he sort of proposes is that maybe there's actually 2 structures and they alternate. Now, of course, today what we would say is that that's a resonance structure. The problem with this, of course, is that, the idea that we always sort of get in our head when we think of resonance is that really it's like, well, sometimes it's this one on the left and then sometimes it's this one on the right. But in reality, remember, it's sort of a blend of those things, and it's neither one of those things at any given time. So it's not like at one moment it's this, and then the next moment it changes to the next one. That in reality, it's something in between. And so what that means for us is that what actually happens in a benzene is that you get these 6 pi bonds here and sort of looping together. And instead of like forming these alternating double bonds that we have, in our Kekule structures here, and that's, by the way, what these bonded structures are called. These are called Kekule structures. What we actually have is really more of a ring where the pi bond there, instead of being like on these 2 carbons and then these 2 carbons and then these 2 carbons, it's actually sort of spread out all over the whole ring. And so it's what we call a delocalized pi cloud. Delocalized meaning that it's not stuck to one atom or even 2 atoms, that instead it sort of circles around the whole thing. And so what we would typically do then is, instead of drawing the Kekule structure here with the double bonds, is we're actually going to put this ring in the middle, and that sort of makes it a little bit easier to tell what's going on there. Now, what's going to matter for us is that really, although a lot of times you can draw these, what's probably best for us, certainly at this sort of introductory stage that we're doing, is that you keep drawing these Kekule structures here on the bottom, because what that's going to do is it's going to let you know that you've got your 4 bonds taken up and that you're drawing things in the right place. What happens sometimes when you draw the little ring in the middle here to show the aromaticity is that you're really sort of losing a little bit of what the structure is and then how it's actually set up. So we don't want to do that. So we're going to stick to our Kekule structures, and your book is going to use similar things. Now, one of the things that is going to drive you bonkers here with aromatic compounds is that, you know how when we did alkenes and alkynes in particular, we talked about how there were a couple of common names that you just sort of have to know because they're going to get used again and again, so like ethylene and acetylene. That is even more true in aromatic compounds. Aromatic compounds was sort of a big branch of chemistry for a long time. And so there's this deep history behind it where they had all of these common names. And what IUPAC did, the International Union of Pure and Applied Chemistry, that sort of gives us our systematic way of doing the names, instead of sort of fighting that, what they basically did was co-opted these in and said, hey, we're going to accept these as names that we can use as well. And so these 10 structures here, these are by far not all of the sort of common ones. But I think that you should probably know these 10. And in particular, I would say that there are 4 or 5 of these even that you just have to sort of know what their common name is. Obviously, benzene is one of them. Toluene is super common. Styrene, that's when we arrange that in polymer form, that's what it's going to be, styrofoam, basically. It comes from that idea. Phenol is another one. We're going to use benzoic acid, benzaldehyde. You can see in lots of chemicals today, and that's sort of that cherry almond sort of scent that you get a lot. And so you just need to know what these common names are. And so I would recommend, as we've done with a ton of things in organic chem, just get yourself some flashcards, make them on your iPad if you want, and just sort of go through these 10 and make sure that you've got these common names. Now, why those common names are important is because the actual rules for IUPAC naming of aromatic compounds, I don't want to say that they're not there or that they're not that important, but in reality there's a bunch of different ways that aromatic compounds tend to get named. And so we're just going to sort of run through the general ways that they get named so that you can recognize those and be able to draw some of those structures. So if they don't have a common name for them, usually we're just going to say that they're benzene, and then we're going to add in whatever is added to it. And so in this case, we've got a benzene ring. It's got a bromine attached to it. We call that bromobenzene. Obviously, if we got a chlorine attached to it, we just call that chlorobenzene, and that would be give us the name there. And again, we would just add on these substituents. If there's a single substituent, if it's a mono-substituted benzene ring, then you just sort of add on what is the substituent, name that, and that will give you the name of the compound. And so we've got ethane basically attached to the benzene here, so that becomes ethylbenzene. This is a nitro group, and that then is going to become a nitrobenzene. So that's for mono-substituent stuff that doesn't have one of these common names back here. And these common names, you can see, they don't necessarily tie right in. I mean, you could say, well, isn't this methylbenzene? And yes, but that's, no one calls it methylbenzene. It's typically called toluene, and so you got to sort of know that name as well. So monosubstituted, just add that on, put benzene at the end of the name. To make matters worse, although we do number sometimes with benzene rings, and I'll talk about that in a second, usually if you only have a couple of substituents, or if you have one substituent and then a common sort of groups around that, they don't actually number them sometimes. Instead, what they do is they number it by the position on the ring. And so if you consider this top position sort of where we would have our first substituent, so if you look at this one, there's a chloro there, then the way it goes is 1 space away from that is an ortho, 2 spaces away is a meta, and then on the opposite side of the ring is a para. And so what that would do is, in this case, this is ortho-dichlorobenzene because there's 2 chlorines, and you've got one up top at the normal position, and then you've got one ortho to that, meaning 1 space away from it. That would also be true if we sort of drug this over here and switch this bond around a little bit. That also is still going to be an ortho-dichlorobenzene. And then, of course, we could change that up a little bit if we wanted to sort of get rid of this name here, and we could move that bond. It would be easier if I hadn't messed it all up there. But if we move that bond down here, then we would have meta-dichlorobenzene. And then if we move the chlorine down here to the very bottom, then we would have para-dichlorobenzene. And I know that's sort of adding an additional level of complexity to it. But again, this is the way that they tend to get named. That's the way that you're going to see those things. You're going to see something like, you know, an ortho-dimethyl, you know, benzene. And so you've got to sort of get those names into your head. And actually, in that case, it would probably be something more like ortho-methyltoluene or something crazy like that. So just sort of keep that in mind. Ortho right next to it, meta 2 spaces away, para on the opposite side. And I think when you see those names, and once we work through a few in class, excuse me, that'll stick with you pretty well. We do, however, use the numbers on the ring. And in fact, I'm sure that given what we've done so far this year, that that's probably what you would prefer to do. And I would agree with you. I think that's a much more systematic way to approach it, is to go ahead and get the numbers on the ring. And so if you've got something like this one that we got here, the way it should work, of course, is that the top one, the top number is essentially going to be 1. And so up where we have our first substituent, that's a 1, 2, 3, 4, 5, 6. Typically, they do tend to work clockwise because we're just going to sort of rotate everything up so that we got one substituent at the top and start counting one from there. And that just sort of makes it a little bit easier. And so you see we've got a methyl at 1, at 2, at 4, and so that's 1, 2, 4 trimethylbenzene. In this case, where you see, well, I've got two different kinds of substituents. How am I going to call that? I can't tetra it because they're different. Well, this is where you go back to the common name. If we just took this part of it without the NO2s, benzene with a methyl group attached to it has a common name of toluene, okay? And so that's going to become sort of our parent word there. And then I've got 3 nitros, okay? And they are at positions, remember the top one is 1, so 2, 4, 6. That's going to give us 2,4,6 trinitrotoluene. And you actually know that compound, whether you know it or not, because that is where we get TNT. The TNT stands for trinitrotoluene. So that is a lovely explosive compound for us right there. Okay? So I know that's a little bit frustrating. Just to throw this last little bit in here, the aromatic groups, or that benzene ring there, can actually be a substituent. So instead of us adding something to the benzene ring, we could add the benzene ring onto something else. So let's say that we had some long, like 20 chain carbon. We would name it according to the 20 chain, and then the benzene ring hanging off of it would be a substituent, just like a methyl group or a chloro group or whatever else, whatever other functional groups that we have. And so the way that works is if it's a simple benzene ring bonded to something, we're going to call that a phenyl group. And then if it's a benzene ring with a carbon in between whatever it's bonded to, okay, so out here is the stuff that it's bonded to, okay, whatever group it's bonded to is out here, then it's a benzyl group. Would it make more sense if this first one was the benzyl group and the second one was the phenyl group? I would probably agree with you there, but that's sadly not what it is. So the single ring by itself is going to be a phenyl group, and then a ring with a carbon in between whatever the group is going to be a benzyl group. And so real briefly, just to show you an example of what that is, this compound, if we took this, so this would be our sort of straight chain alkane here. That would be pentane. And then hanging off of the pentane is our phenyl group, or is our benzene ring. And so it's hanging off at the second position, right? And so that's going to be 2-phenylpentane. You could conceivably actually name that according to the benzene with that substituent as well. And in that case, we would call it pentylbenzene. There's still a 2 there to let us know that it's attached to the second in the pentyl. I think normally we would probably do the phenylpentane thing, but either one of these would be acceptable. And again, I know you're thinking to yourself, this is insane, the naming for this. And again, this is what makes organic so difficult. And it gets particularly difficult here because we sort of strayed a little bit from these are the rules, follow these rules all the time, and as long as you know the rules, everything will work out okay, to, hey, you got to remember all these crazy names that aren't necessarily, strictly speaking, part of the rules. But that's the world of organic chem, and so that's why you want to get those flashcards, run through that stuff, and then obviously, of course, we'll work through a ton of these in class to make sure that everybody's got a pretty good handle on this. All right? Thanks, guys.